Okay, here's some more examples. We're going to be looking at the example when we have a power, an exponent, a power raised to another power. And so here's the rule here, and let's just apply the rule in this case. So in the previous examples, we did the math without the rule, and so in this case, let's apply the rule and then think about why the rule works. So in this situation here, 5 cubed times 5 squared. If I'm following the rule here, looking at what this example is saying right here, a to the power of m raised to the n is equal to the a to the power of m times n. Just multiply them. What this then becomes, again, students get confused why we do it, but the answer is 6. This one would be 7 to 32. And again, now I want you to think about why, the why question. Why does this work? So that you can understand this and not memorize. And so 5 cubed squared really means 5 cubed times 5 cubed. And so then we have a rule where we just add the exponents now. Or again, you could say that just means 5 times 5 times 5 times 5 times 5. So every rule or shortcut or formula theorem like this has a why to it. Why does it work? And so now you can see I have the number 5 6 times. The base has now occurred 6 times. And so that's why that rule emerges where you end up just thinking, what does it actually mean there? And then this one here, I'm not going to write it out 32 times because it's just too long. So that's where the shortcut emerges. Think about it's in the book. Think about what is the proof? Why is this the case? Is there a proof? Proof meaning, can you do something like this where it shows you that answer? I want you to look that up in the book. Take a look at that proof. Why does that? The book has it after theorem 3.3. Take a look at that and see why that would be the case and how they end up writing that. Okay. Let's go on to the second example here. The other one is when we're dividing numbers, for some reason we subtract exponents. And so let's apply the rule again here. So the rule quickly would just be 5 to the power of 4. In this case, it would be 7 to the power of 3. That's it. Done. Look how fast it is. Now it gets back to why again. Why does that work for those, right? And so let's do one together. So 5 to the power of 7 over 5 to the power of 3. Why are we subtracting? Because again, back to this idea of one-to-one correspondence. That was one of the first things we learned in this class, and you probably thought, why are we learning that again? What does that mean? It was because it was kind of a complicated definition. We look at this, and then what happens is that the one-to-one correspondence, right? Each of these become a 1 because you're dividing 5 divided by 5, 5 divided, they match up. And so then what you're left with is this group of 5s here. How many? 5 to the power of 4. And again, because of the one-to-one correspondence, they end up canceling each other out. And again, what does that proof look like? You can look on in the book. I want you to at least read that so you're familiar with it. Challenge yourself to do that, please. And so those are the two, the an exponent raised to an exponent rule, and then we also then have the division rule. So we have the product rule here, or the power rule is called, and then this is called the division rule here. So that's what we got.